In Chapter 12, we're going to start talking about quadratic functions. And in this first section, we're going to look at quadratic functions and their graphs, what the quadratic function looks like, and what the graph of a quadratic function looks like. So if you remember back at the beginning of Chapter 11, when we started talking about polynomial functions, we talked about a function of degree 2 is called a quadratic. Okay. So when we start talking about these, a quadratic function is nonlinear, which means it's not going to be a straight line. Okay? And it can model a rate of change when that rate is not a constant. Okay? The graph of a quadratic function is going to be symmetric. Okay? It's going to be a curve with a high point or a low point. So as we start getting to look at these, we'll see that they have a U shape to them. So when we talk about a quadratic function down here at the key concept, it's a function that can be written in the form of y equals ax squared plus bx plus c, where the a is not equal to 0, because if a were 0, then we'd have no squared term and we'd be back to a linear equation. So this is what we call the standard form of a quadratic function. And down here are some examples. It could be just a 3x squared, it could be an x squared plus 9, or something like x squared minus x minus 2. Those are all examples of quadratic functions because they all have the highest degree being a degree of 2. The most basic or the simplest of the quadratic functions, written in this function notation of f of x equals x squared or y equals x squared, is what we call the parent function, or sometimes it'll be referred to as the base function. Okay? And the graph of a quadratic function is this U shape that we see over here to the right, okay, that's called a parabola. Okay? So the parabola that's shown is the parent function of y equals x squared. Notice that it has a low point that is sitting at the origin at 0, 0. Okay? And notice that you could fold it along the y-axis here, and if you were to fold it on that y-axis, it's kind of like a mirror image on either side. If we folded it, the two sides would match up perfectly. So in this case, this y-axis here is what we call an axis of symmetry. It's kind of a center line that cuts the graph directly in half, and both sides are the same. When we talk about this low point down here, the bottom of the U, the highest or lowest point of the graph, if the graph is upside down, is what we call the vertex. Okay? And the vertex is always going to be on the axis of symmetry. Okay? So when we've got this standard form of a quadratic equation, this ax squared plus bx plus c, if the a is greater than 0, if it's positive, then that means the graph is going to open upward. And therefore the vertex is what we call a minimum, or the lowest point of the graph, or the parabola. If the a is less than 0, meaning the a is a negative, then that means that graph is going to open down, so it's going to be more of an upside down U, meaning the vertex is now the highest point, or the maximum of the graph. So it is the highest value that the function will have. Okay? So there's going to be a lot of vocabulary in this section here, so we want to make sure that we're getting these definitions down and we're able to identify and know what these different words are talking about. So if we look at these couple examples here, just simply looking at a graph and trying to identify the coordinates of the vertex. Where is that vertex point? And is that vertex a minimum or a maximum for the graph? So if we look at example A here, the vertex, remember, is always the highest or the lowest point. So in this case, that vertex is sitting right up here. So the vertex in part A is at 0, 3. Okay, 1, 2, 3. And since it is a high point, we would say that it is a maximum. In part B, we can see that that vertex is a low point right here at x being 1 and y equal negative 1. So here my vertex is at 1, negative 1, and because it is the lowest point on the graph, we say that that vertex is a minimum. So if we look at this graph to the right, what is the vertex and is it a minimum or a maximum? Okay, so see if you can identify those and then check them with the video. So here is our point at -2 and -3. So my vertex is at -2, -3, and it is the lowest point, which means that it is a minimum for the graph. How about in problem number 1 down here? Identify the vertex of each parabola and again decide if it's a min or a max. Well, in problem 1, our vertex point here is going over 2 on the x and is going up 3 on the y. So our vertex here is the point 2, 3, and because it is a high point, it is a maximum. Okay. Now number 2 is a little bit different. We don't have a graph, we have a table. So we have to use this idea of the symmetry. And if you look at the y values of the graph, you'll see the symmetry. You'll see that from 0 here, as I go to +1 on my x, the y goes to 2. And the same thing happens when I go down 1. When I go up another one, it goes to 8. And this one goes to 8. So on either side of y being 0, the graph is exactly the same. And notice that these values are increasing, 0, 2, 8, 0, 2, 8, which means my vertex is going to be at the point 2, 0, and it is going to be a minimum because all of the other y values are getting bigger as I move away from the 0. So we can also look at a table of values and sometimes see where that vertex is by looking at that symmetry that exists in the y values. So when it comes to making the graphs of these parabolas, sometimes it's possible to use that symmetric property of the graph to quickly generate it. So once we know where the vertex is, then we can choose some points on one side of the vertex and use that idea of symmetry to just reflect them and to get the other side of the U-shape. So if we look at this example here in problem 2, the function is y equals 1/3 x squared. So because it's just that ax squared form that we have up here, whenever it's the ax squared form, the vertex is always going to be at the origin. So we know we're going to have the point 0, 0 as our vertex. So notice our x values that we're choosing. We're just choosing some values to the right of 0. And the reason we're picking 3 and 6 is because they are multiples of 3, and having that 1/3 fraction, we want to make sure that we're able to get multiples of 3 for my x squared so that I'm not trying to graph decimals. If it were a 1/2 out front, then I would pick x values that are multiples of 2. If it were a 1/4, I would pick x values that are multiples of 4, and etc. So when I put in an x value of 3, notice I'm getting a y value of 3, meaning the point 3, 3 is a point on my graph. And that's this point right over here. When I put in 6, I get a y value of 12. So we've got the point 6, 12, which is this one up here. Now, using the fact that the vertex, which is at the origin, sits on that axis of symmetry, we can look and see that this point was 3 units to the right, so I would have a matching point 3 units to the left. This point up here was 6 units to the right of the axis, so there would be a matching point 6 units to the left. So I would also have the point -3, 3, and I would also have the point -6, 12. And that gives me my symmetry and allows me to sketch that parabola. Okay. The other thing that we need to make sure we're talking about is this idea of domain and range, which you probably talked about back in Math 1 or in Algebra 1. Okay. Remember that the domain has to do with the x values. Okay. What x values are we allowed to use in the function? And the range has to do with the y values that we're going to get out. Okay. So remember that domain can often be thought of as input, the values I'm allowed to put in, and range can be thought of as output, the values that I'm going to get back out, which are the y's. So for this quadratic function, being that it is the function of 1/3 x squared, the domain is all real numbers because I'm allowed to put in any number for x. I could square any number. So any value of x could be chosen to put into my table here for my x values. The range, which is the output, if we look at the graph, we can see that the lowest value we have for the y is 0, and then everything else is heading up, okay? Which means the range is going to be all y's that are greater than or equal to 0. Okay? And when we talk about this parent function of y equals ax squared, or the parent function of y equals x squared, its domain is the same thing. The domain is going to be all real numbers, and the range is going to be all y's that are greater than or equal to 0. So that's kind of the basic starting point for all quadratics. So unless the graph moves, that's always going to be my domain and range. So here's one where we've got this function y equals negative 3x squared. We want to sketch the graph, and we want to identify the domain and range. Okay. So the first thing we're going to do is we're going to set up our input and output table with our x's and our y's. Now, looking at the function, being it's of that form of y equals ax squared, we know that it's going to have a point 0, 0, that the vertex is going to sit on the origin. We also know that since the a is less than 0 here, that it's going to open down. Okay, so the graph is going to be kind of an upside down U when we get there. So we know those things going in. So we're going to pick some values. If I choose 1 and I put 1 in for x, then I'm going to get a negative 3 for y. If I pick 2 and I put 2 in for x, then 2 squared is 4 times negative 3 gives me negative 12. So you can see that even though x only increased by 1, our y value is changing quite a bit from negative 3 to negative 12. So we're going to use that idea of the symmetry, and we're going to sketch the graph here. Okay, so we're just going to make kind of a small sketch here. And here's my x-axis, and here's my y. I've kind of skewed it a little bit because I know that I've got the vertex at 0, 0. I've got 1 and negative 3. And then when I go over to 2, I'm going to be all the way down here at 2, negative 12. And this is going to be the point 1, negative 3. Okay. So far, I've got kind of this part of the graph right here. Now, if I use this idea of symmetry, since I know I have a point that's 1 unit to the right, I'll have a matching point 1 unit to the left. I've got this point down here that was 2 units to the right, so I'd have a matching point over here 2 units to the left. So I'd also have the point negative 1, negative 3, and I would also have the point negative 2, negative 12, which would allow me to sketch in the other half of my parabola. So I don't have to pick a great deal of points. I need to know where the vertex is at, okay, 0, 0, and I pick 2 points to the right, and then I use the symmetry to come up with those 2 points on the left that allows me to complete that kind of that U shape. Okay. Now what we'll start to notice, and sometimes it's easier to see when you're using graph paper, okay? This was the graph of negative 3x squared. And what we'll start looking at here in the very near future is that what this value of a is going to do to the graph. Okay, if that value is a fraction, it changes the graph in one manner. If it's an integer, it changes it in another manner. Right now, all we're looking at is that if it's positive, that the graph is going to open up, and if this number is negative, notice it makes that graph, it turns it upside down and opens down. So my vertex here now is a maximum because it is the highest point on the graph. Okay. If I were to look at the domain of this function, again, the domain is going to be all real numbers because I could put in any value I want for the x. But the range, however, notice that the range is now going from 0 and all my y values are going down. So the range are all the y's that are less than or equal to 0 because we flipped that graph over. Okay. So some key things that we need to know here. We need to know what the parent function looks like. We need to know how to identify the vertex and whether that vertex is going to be a maximum or a minimum. We need to kind of be able to understand the idea of axis of symmetry, that the name of this graph of a quadratic is called a parabola, and we also need to know the idea of domain and range and be able to identify the domain and range for a function. Okay? So in class tomorrow we'll do some more work with all of these things and kind of get used to all this terminology and all these new definitions that we're going to have to know in order to move forward through chapter 12. We'll see you then.